Ladies and gentlemen, you are all welcome to my YouTube channel. So, in today's video, we are going to look at the concept of half-life. Although I have actually made a video on the concept of nuclear chemistry, radioactivity, and nuclear reaction. I also have a video on radioactive decay. So, in this video, we are going to look at the concept of half-life, which is a continuation of nuclear chemistry. So what is half-life? A half-life is a time taken for a radioactive substances to decay to half of their original mass. That is what we call half-life. The time taken for a radioactive substances to decay to half of their original mass, that is what described as half-life. Like for example, let's say you have sample A and the mass of sample A is, let's say, 80 gram. And the half-life for this sample A, let's say the half-life, we represent half-life with T half. So we use T half to represent half-life. So let's say the T half, that is the half-life of sample A, is 10 days. The half-life of sample A is 10 days. That means that after every 10 days, the mass of sample A will decay to half of its original mass. So let's say, since we say that the mass of sample A is 80 gram, so after 10 days, after 10 days, sample A will now decay to half of its original mass, which is 40 gram. Because the original mass of sample A is 80 gram and the half-life is 10 days. And according to the definition of half-life, we define half-life as a substance, is a time taken for a radioactive substances to decay to their original mass. Let's say we have an element A, that's radioactive element A. So if the half-life of that particular element A is 80 gram, so it means that after 10 days, the mass or the original mass of that radioactive substances will decay to half of its original mass. And that is what you call half-life. So in this case, we have sample A and the half-life for sample A is 10 days. So after 10 days, the mass of sample A will now decay from 80 gram to 40 gram after 10 days. And after additional 10 days, this 40 gram will also decay to another 20 gram. So after every 10 days, the mass of this sample A will be decayed to half of its original mass. And that is why initially we have 80 gram of sample A, and after 10 days it now decay 40 gram, and after additional 10 days it decay to 20 gram. And moreover, after another 10 days, after another 10 days, this 20 gram will also decay to 10 gram. Then after additional 10 days, it will decay from 10 gram to 5 gram. So this is what we call half-life. So a half-life is a time taken for a radioactive substances or radioactive material to decay to half of their original mass, and that is what you call half-life. So the mass here, the starting mass here is called initial mass, or you can call it original mass. So let's call it here original. Let's call it as original mass. Original mass. We call it original mass. That is the starting mass. The starting mass is called original mass. while the mass left after this series of the half-lives is called mass remaining. Mass remaining. And that is what we call, so here we have two important parameters. We have original mass, that is the starting mass, and then we have the final mass after the series of the half-lives, which is called mass remaining. And in addition, we have also the number of half-lives undergo by the radioactive material. So therefore, now by looking, we can now calculate the number of half-lives. So first, we have 1 here, we have 2 here, we have 3 here, we have 4. So this is what we call N, written as N. And this N represents number of half-lives. And in this case, the number of half-lives, because we have 4 different, or the sample A here undergo 4 different half-lives. So therefore, the number of half-lives is equal to 4. It's equal to 4. In fact, we can actually use a formula to calculate the number of half-lives. Like for example, these are the half-lives. So if you take them, if you sum them together, we can actually call them decay period. That is the number of decay period. So we can call it decay periods. Decay periods. We can call it decay period. So here we have a decay period. So how are we going to know our decay period? Is by adding the total number of the half-lives undergo by the sample A. So here we have 10 plus 10 making 20 plus 10 making 30 plus 10 making 40. So it means that the decay period is now equals to 40 days. We have now 40 days as the decay period. And of course, we have the half-lives. So the half-lives here, the half-life here is equal to 10 days. We have 10 days. So you can now calculate the number of half-life by taking a ratio of decay periods to half-lives. So therefore, now we can now say N is equal to decay periods divided by the half-life divided by half-life. So now our decay period is 40 days. So we now have 40 days divided by 10 days. And this will now going to give us 4. So we now have 4 here. So this is one of the important formula that we use in calculating or in a calculation of half-life. And we also have another formula that we can have a situation where we will be asked to calculate the fractional remaining. You will be given the half-life. You will be given the number of half-lives undergo by the radioactive material, and then you will be asked to calculate the fractional remaining. So how do you now calculate the fractional remaining? We have a formula. Fractional remaining so we have fractional remaining is equal to 1 all over 2 power n. So in some cases, we'll be given the number of the decay period, we'll be given the number of half-lives, and then you will now calculate the number of half-lives undergo by the radioactive material. So therefore, if you have that, you are now going to, if you want to calculate the fractional remaining, then it's now equals to 1 all over 2 power n. So here, you now have two important formula. This is number 1, and then this is number 2. And then in addition here, we have mass remaining and we have original mass. So sometime we will be only be given mass remaining, you will only be given mass remaining and you will be asked to calculate original mass, or in some cases you will be given the original mass but to calculate mass remaining. So therefore, in addition, we also have a formula for calculating that. We have a formula for calculating that. So therefore, the formula for calculating mass remaining is going to be, as I said, mass remaining and the original mass. So mass remaining is now going to be mass remaining is equal to original mass. Original mass, we have original mass all over 2 power n. So this is also another formula for calculating mass remaining. So mass remaining is equal to original mass all over 2 power n. So this formula is also very, very important in calculation of half-lives. Then we also have another formula. Generally in radioactivity, we also have what we call we have different types of reaction. We have first order reaction, we have zero order reaction. So for the zero order reaction, we have a formula that we can use to calculate the half-life for zero order reactions. So the formula for calculating zero order reaction is given as the formula for calculating zero order reaction is equal to 1 all over K into A plus bracket not here. So therefore, K here stands for rate constant. The K here stands for rate constant, while A naught here stands for the initial concentration. Initial concentration. So we have this as initial concentration. So then after this, so this is a formula that is used in calculating zero order reaction. A formula for calculating half-life of zero order reaction. We also have a formula for calculating first order reaction. We also have a formula for calculating first order reaction. So for the first order reaction, the half-life is equal to 0.693 all over epsilon. And then the epsilon here stands for decay. Sorry, this is lambda. This is lambda. So the lambda here stands for decay constant. So ladies and gentlemen, these are some of the important formula that are used in calculating half-lives, and they are very, very important. And in this video, you should not actually forget with these 4 different formulas, because I know that it is going to help and solve a lot of problems. Number 1, we started with the definition of half-life, which actually defined as a time taken for the radioactive substances to decay to half of their original mass. So here we have sample A, and sample A here have a mass of 80 grams, and the half-life for sample A is 10 days. It means that after every 10 days, the mass of sample A will reduce to half. So therefore, that is why here we have 80 grams, then after 10 days, it reduced to 40 grams, and after another 10 days, it reduced from 40 to 20 grams, and after another 10 days, it reduced from 20 grams to 10 grams, and after 10 days, it reduced from, after another 10 days, it reduced from 10 grams to 5 grams. And the starting mass is called original mass, while the final mass is called the mass remaining. And of course, we have a formula for calculating the total number of half-lives undergo by radioactive substances. Like for example, in this case, this sample A undergo 4 different half-lives. So 1, 2, 3, 4, and that is why we have this 4 here. And then the next one is actually a formula that you can use, that you can simply use to calculate the number of half-lives by taking the ratio of the decay period by half-life. And of course, we use it here because the number of half-lives here on the go is 4, and we sum them together, which give us a total of 40 as the decay period. And then the half-life is 10 days. So we now take 40 divided by 10, which gives us 4 as the total number of half-lives. And then we also have a formula for calculating fractional remaining, which is 1 all over 2 power n. And then in addition, we also have a formula for calculating mass remaining or original mass. The formula is mass remaining is equal to original mass divided by 2 power n. And then we also have a formula for calculating different types of reaction and their half-lives. So for the zero order reaction, we use T half, that is half-life is equal to 1 all over K times A in brackets then epsilon. So the K here stands for rate constant, and then the A here stands for the initial concentration. And then we also have a formula for calculating half-life of first order reaction, which is T half is equal to 0.693 divided by lambda, and the lambda here stands for the K constant. So ladies and gentlemen, in the next video, we are going to look at some examples and the calculation of half-life. And if this is the first time you are coming to my YouTube channel, please subscribe.